Hi, I'm Maurice Smith, and I'm introducing optimal control day here at Neuromatch Academy. I'm a faculty member in the School of Engineering at Harvard, and I study learning and memory in the motor system. Now, this may seem a bit random, but I really like trees, and I'm going to start off by talking about them for a minute. Trees are arguably the most successful life forms on Earth. Collectively, they constitute 99% of the world's biomass, and they're also the world's longest living life forms. This is a bristlecone pine from the White Mountains in California. The oldest one, whose identity is kept secret to protect it, is a staggering 5,000 years old. Trees are also the largest living things on Earth. Here's an absolutely majestic California redwood rising 100 meters into the air. And here's a closely related giant sequoia named General Sherman in Sequoia National Park, also in California. That's the biggest individual tree in the world by biomass. It weighs 5 or 6 times more than the world's biggest animal, the blue whale. And in case you missed it, those little dots in the bottom corners of the photo right here are people, providing a sense of the enormous scale here. Trees can, of course, also be quite beautiful, like in this photo of the foliage turning color in the fall in Harvard Yard in Cambridge, Massachusetts, where I live. So trees have a lot going for them. They're the largest, the longest living, and arguably the most successful life forms on Earth. And on top of that, they're beautiful. But there's something apropos to this course that trees don't have: brains. But why is that? Now, why questions are difficult to answer definitively, but thinking about this little squirrel perched high in a tree branch might give us some insight, as she and all other squirrels like her have well-developed little brains. And with their brains, squirrels can do a number of amazing things, like this little guy raiding a bird feeder, and this one scampering on top of a fence, and this one leaping across an open gate. These are all examples of quick, exceedingly nimble actions that must be well planned and controlled. And to me, this points us to the answer as to what brains are for. I'd say that the reason we have brains is to allow us to plan, control, and coordinate quick, nimble motor actions. After all, it is only through their actions that organisms can interact with the world and improve their chances of survival. And so the other things that our nervous systems do, like sensory processing, inference, and higher-order cognition, ultimately are only performed to enable better planning and control of our actions. Now, trees and other plants that don't have brains can produce some actions like phototaxis, which is the ability for their leaves to slowly orient to the sun as it arcs through the sky each day. And on even slower timescales, plants tend to grow their branches towards gaps in the canopy that let light through, and grow their roots towards wetter ground. But there's a degree of control here. So there's a good degree of control here, but probably no planning, and it's hard to really call any of this quick or nimble. Now there's the case of the Venus flytrap. This plant can snap close to capture an unsuspecting insect before it has a chance to escape. But the control here entirely comes from the physical mechanics of the trap, and planning doesn't really apply. So it seems like having a brain may indeed be key for allowing us to plan, control, and coordinate quick and nimble motor actions. To seal the deal, we can consider this creature, the sea squirt. When a mama sea squirt gives birth, her babies actively swim around looking for a place to plant themselves. After they find it, they begin the transformation to an adult form that feeds passively while anchored down for the rest of its life. What's really interesting, though, is that early in this transformation, the sea squirt ingests most of its nervous system. Again, in line with the idea that the raison d'etre for our brains may be to enable the planning and control of quick and nimble movement. Okay, so now let's get to talking about the optimal control of actions in particular. Before we can delve too deeply, however, we'll set up a mathematical framework to guide our discussion. We'll base this framework on the dynamical systems perspective. And so we'll say that there's a dynamical system to be controlled that can be described by its state S. For instance, if we have a rigid object that's moving through the air, we can describe its state by its position and velocity. So there'll be 6 state variables, in that case x, y, and z position, and x, y, and z velocity. If you want to be even more complete, we could add state variables for the orientation of the object, and so we could have a total of 12 state variables: x, y, z position, x, y, z velocity, the 3-dimensional orientation, and the 3-dimensional angular velocity of the object. And so with that in mind, the general equation that would dictate the system's dynamics would be that the rate of change of the system's state, s dot of t, is equal to what we call the dynamics of the system, this function d of the state. We can also have a linear version of this where the change in state is equal to a constant gain d or a constant gain matrix d simply multiplied by the state. All right. But both of these equations, the change in state is entirely provided for by as entirely a function of a single sort of internal state variable. And so we call these cases those autonomous dynamic systems. What we're going to be sort of more interested in for this lecture are dynamical systems with an external input, so-called non-autonomous systems, where there's an external input A, and so the change in state here would be given by this dynamics function d of both the state S and this external input A, where A is, you can think of A as an action taken on the system that will change how the state evolves. We also have a linear version of this, where the change in state S dot of t would be equal to gain or gain matrix D multiplied by the state plus some other linear gain matrix B multiplied by the action. And so this brings us to the control problem, where we want to choose some action input to the system, A of t, such that we can get S of t to be equal to some S star of t, where S star of t is a desired state behavior. Before delving into this too rigorously, go through an example problem that will illustrate some of the key ideas involved. So let's look at this cartoon example where we bring back our squirrel from earlier. We can imagine that our squirrel is sitting in a tree without any acorns in it, but he's hungry, and so he desperately wants to eat an acorn. Luckily, he sees a big fat acorn in the tree across the way, and so the squirrel might be thinking something like, I want that acorn right now. Now, of course, getting this acorn exactly now is impossible, and so the squirrel could back off just a little bit in his demands and think, well, I want this acorn as soon as possible. And if that were true, the squirrel might be able to solve the control problem by taking an action where he jumps over to the adjacent tree to be able to eat this acorn. Now, a control engineer would view this action a bit differently than a normal person would. Whereas instead of focusing on the idea of jumping, the control engineer would focus on the details of how to execute this jump. To be able to jump, the squirrel is going to need to activate the muscles in his hind limb, and in particular produce just the right pattern of activation across those muscles with just the right intensity that the squirrel would launch himself into the air with just the right angle and just the right initial velocity that he could land safely on a branch adjacent to that juicy-looking acorn. And so he could eat it as soon as possible. A more thoughtful squirrel, however, might have a more complicated goal in mind. For example, he might think that I want that nut as soon as possible, but without being too foolhardy or using too much energy to get it. And so not being too foolhardy would maybe save the squirrel from slipping out of the adjacent tree if he can't quite jump far enough to it, or if there's an unexpected gust of wind. Not using too much energy would allow the squirrel to be able to get to his nut perhaps more efficiently without resorting to the intense energy expenditure that a big jump might require. And so if the squirrel had those goals in mind, he might take a completely different path to get to his acorn. He could instead climb down from the tree, scamper across the gap, and then climb up the tree with the acorn in it. So control need not be single-minded, and in that there may be multiple goals that we strive for simultaneously. Now let's think about how to put these ideas into a more rigorous mathematical formulation. The exact control problem, which might not be possible to achieve, would be to choose some action A such that the squirrel fully matches his desired state. And now if you can't do that, you can have a looser version where we can choose some action A of t such that the achieved state S of t is approximately equal to the desired state S star of t, but not exactly. And we can quantify what approximately means here. By choosing A of t so that there's a cost that's dependent on the error between the actual state and the desired state, which we want to make as small as possible. In particular, here we have a cost that's the integral of the square of the difference between the state that's actually achieved and the desired state. So it's some sort of accumulation of the magnitude of the state error across time. This formulation can be naturally extended to incorporate multiple goals. The idea would be to simply define a new cost, or a new cost function, that is not only a function of the state error, but also of the other goals, like energy expenditure, which could be included by adding a term for the amplitude of the action itself here. The first term is a state error cost, which is a cost that comes from having a difference between the achieved state and the desired state. And the second term is an action cost that describes a penalty for how much effort we put into achieving our goals. Other terms, like a safety term that penalizes potential danger rather than effort, could also be included if we want. So how can we go about choosing the control variable A optimally? The most basic way we could do this is what's called open loop control. And so here we choose A of t entirely as a function of the desired state. And since the desired state is known before we begin acting, then A of t can be pre-computed, which is very nice. In order to figure out how to do this, we just look back a bit. The general form of the state equation says that S dot of t is equal to the dynamics function d of S of t and A of t. And if we solved for A of t, we could get that this A of t is the inverse dynamics of the desired state and the desired change in state. For the simpler linear case, we can solve this out even more specifically. And if you recall, the state equation for the linear case, it says that this change in state S dot of t is equal to a constant gain matrix D times the state S of t plus a constant gain matrix B multiplied by the action A. If we solve this out for the action, we get that the action A is equal to the inverse of B multiplied by the difference between the desired change in state and the rate of change of the desired change in state, and d times the desired change in state. In the closed loop case, things get a little bit more complicated, however. So what we have is that the idea for the closed loop control is it will base the control action A of t on both the desired state and on the actual state that we experience as we're performing the control. Here we're implicitly admitting that the actual state we experience at each time point may be different from what we planned on experiencing. Thus, the action A of t will be continuously updated based on the state S of t where we're actually experiencing. This allows us to customize the control and route based on the details of the situation that we currently find ourselves in. This is often called closed-loop feedback control because info about the state S is fed back into the control function. Okay, so next I'm going to visualize the process of open-loop and closed-loop control for you. So for open-loop control, recall that what we have is an action A of t is going to be equal to the inverse dynamics d to the minus 1 applied to the desired state. Okay. We can illustrate this with a block diagram where we take the desired state S star of t and how we would like it to change S dot star of t as inputs to a controller block, which is the model of the inverse dynamics function d to the minus 1, generate an optimal action A for us. Then this control action A of t is applied to the dynamical system D that we're trying to control, and then the output will be the controlled state, which corresponds to the results of our optimal control. Here. For closed loop control, we have a similar but somewhat more complicated picture that extends the open loop control that we just discussed. The main idea is that the feedback of the state actually experienced S of t is going to be used to improve our controller. More specifically, if we have a block diagram where the difference between the actual state S of t and the desired state S star of t, right, are computed to make an error signal, which is then fed back into a feedback controller that can be used to alter the feed forward motor command A of t. And this sort of feedback can improve the performance of the system because, again, we're taking, we were able to account for these errors between the actual state S of t and the desired state. What's not so immediately clear in this diagram is, at least for biological systems, this sort of feedback comes with a host of delays associated with it. And so these transformations and computations of the information involved in the transformations aren't instantaneous. And so there's sensory delays in somehow getting sort of neural imprints of the controlled state information that we'd like. There's some delays associated with computing the error signal by subtracting the controlled state from the desired state, and there is and there can be errors in implementing the sort of feedback control of the error signal to generate a supplementary motor command that can add on to the A of t that's originally present. These delays, at least in total, can range up to 200 to 250 milliseconds, especially if visual information is involved in sensing the state of the system. For a biological example of open loop control, we can consider the case of our squirrel leaping forward out across the gap from one tree to another to go after that juicy acorn. Quickly springing off the tree branch might take 100 milliseconds or less, resulting in an action that is open loop in nature. This is the case because the latencies incurred in generating feedback-based corrections would exceed 100 milliseconds, and so by takeoff, the squirrel would not yet have had the time to construct corrective motor commands for any information about the motion that took place since the beginning of the leap. And so we can call this an open loop or ballistic movement. If an action unfolds over a longer period of time, feed-forward and feedback control could coexist. At the beginning of an action, we'd have some feed-forward control for motor commands coming from motor regions of the brain and going down the spinal cord, and then traveling down lower motor neurons, say maybe to muscles in the hand or arm to be controlled, that would result in, say, some finger motion, before any sensory information from the action has had a chance to influence these commands. But then as action proceeds, sensory feedback from the ongoing movement in the control limb will travel from the limb itself to the spinal cord and then make its way from the spinal cord into the brain. We might also receive visual feedback about the movement. This feedback information can then supplement the feed-forward motor command with a feedback-based component that might be useful in correcting errors in the ongoing movement. To me, one of the most exciting things about computational neuroscience is the idea that one can leverage a deep computational understanding about how problems that might be important for the nervous system can be solved in order to gain insight into neural function. In line with that, we can take this schematic about how optimal control can be performed and use this to ask questions about neural function. In particular, we can ask questions about how a feed-forward controller that models the system's inverse dynamics can be updated when those dynamics change, about how errors that are estimated in error signals, and about how similarities and differences between feed-forward and feedback controllers. For example, we can see that feedback controllers, like feed-forward controllers, must act through the system's dynamics. And so we can ask questions about how models of dynamics are formed and adapted in the nervous system for both types of control, and whether models that rely on shared or distinct information proceed for these types of control. To answer these questions, one approach would be to experimentally alter the system dynamics and then obtain data on how this control system responds. One way to do this would be to physically alter the dynamics of the environment. Here's an example called the force field learning paradigm. In this experiment, an individual is holding a robotic arm that can produce forces here as shown in the X and the Y directions as movement takes place. And so in comparison to movements at a baseline where robotic forces are effectively turned off, what we can do is program this robotic arm to produce a pattern of forces that we call a force field, shown by the black arrows to the left here. Here, we call this a force field because the force during the movement is a function of the motion itself. And in particular, here we're using a force field where the force is directed perpendicular to the direction of motion, or orthogonal to it. And the amplitude of the force is proportional to the velocity of the ongoing movement. The velocity is largest in the center and smallest at the ends. Okay. Well, we can have another type of trials called air clamp trials, or air clamp movements, where there are large forces that are spring-like in nature and restore the movement towards a straight line path to the target if it were to go astray in the lateral direction. This is useful because here these forces make it so that errors in the ongoing movement will be kept small, and therefore the size of the feedback responses will be kept small, and this allows us to closely examine feed-forward motor control. So here's some data from selected air clamp trials that go from early to late in the force field learning paradigm. Okay, so here most trials are force field learning trials, and the subject sort of learns to compensate for these forces, and then forms a model of the force field dynamics to control their movement. And the trials are ordered from early to late, going from sort of light gray to dark gray in color. So full compensation, or desired sort of force profile that subject would produce, is just shown in green here. And what we see is that early in learning, the subject makes a compensation that's about half of what's needed to fully compensate this force field. Okay. Each trace here represents the air clamp trials that occur in 15 movement bins, from the first 15 to the last 15 out of 300 trials here. What we can see is that after this quick sort of initial learning from the first 15 or first 30 movements, there's a more gradual sort of improvement later. But what's interesting is that there's not just sort of a gradual sort of increase in the transient forces that are required to compensate for these sort of transient green dynamics. Is that there's also an increase in specificity in the patterns of these forces. So whereas the early forces include sort of an inappropriate sort of static component that's not there in the green sort of dynamics, what we see is that as the learning proceeds, the transient component of the adaptation increases, just as the sort of inappropriate static component decreases, making the sort of the shape of what's learned more appropriate for the dynamics. And so the dynamics sort of more closely matches the structure. The learned dynamics in gray or in dark gray and black more closely match the structure of those sort of the green dynamics that are in the environment. Here's data from a study in which human participants first learned novel dynamics without experiencing unexpected perturbations. And then, after this feed-forward learning took place, large perturbations were applied to measure feedback responses. What we're measuring here is the extent to which the feedback response incorporates the novel dynamics that were just learned. Now, without going into too much detail, perturbations were applied between 0 and 100 milliseconds. And what you can see here is that there's very little response in the first 200 milliseconds after perturbation onset. But after that, the nervous system really matches what the dynamics of the environment are in its adaptive response, suggesting that these feedback responses can incorporate learned feed-forward dynamics without specific training for the feedback responses themselves. There's also evidence that feedback control can be disrupted independently of feed-forward control during neurologic disease, in particular in a neurologic disorder called Huntington's disease, which affects the basal ganglia. And evidence comes from this looking at the jerkiness of movements during their time course. Jerkiness is a measure of the smoothness and quality of a movement where lower jerk corresponds to smooth, high-quality movement. What you can see here is that subjects who are symptomatic for Huntington's disease in red, or asymptomatic for it, but clinically have the gene for it in orange, have really identical jerk profiles compared to controls for the first 250 milliseconds or so of the movement, but where the movement is entirely open loop. But after that point, their jerk profiles really diverge from what the controls shown in blue look like. Okay. This suggests that the problem that they have in their motor control is specifically with feedback control, because it's only when the feedback corrections take hold do their jerk profiles sort of diverge and worsen compared to healthy controls. You can test this idea by looking at challenging these feedback responses with large perturbations. And so here's some data from healthy controls in a sort of center outreaching task. And so here there are 8 movements shown that start in the center and go to 8 sort of peripheral target locations. So what's shown here are perturbations or movements that are unperturbed. There's 0 Newton perturbations applied, compared to movements with medium-sized 12 Newton perturbations and large-sized 18 Newton perturbations. And so for simplicity here, I'm just showing the perturbations that are sort of acting sort of down and to the right. And what you see is that when there are medium or large perturbations applied, these perturbations are substantial and that they can sort of push movements off course by, say, 3 or 4 out of the 10 centimeter movement duration. But these healthy controls are able to really sort of correct these perturbations with great aplomb. And so these sort of corrections are smooth and direct to the target sort of over and over again. Right. However, in subjects with Huntington's disease, there are many movements where the feedback responses become sort of wildly disordered. So I've highlighted some of these sort of the most sort of peculiar examples in colors here. And you can see for this particular movement, as after it's perturbed off course, the feedback response sort of wildly oscillates before it gets back to the target. Here, after this one, is sort of a milder oscillation, but much greater than anything you see in controls. Here's another example where the movement correction was wildly perturbed, and here's another in pink down here. Okay, so what we see here is evidence that in the the neurodegeneration that happens in the basal ganglia for Huntington's disease that specifically affects sort of online feedback responses and leave these sort of the feed forward motor commands that have longer preparation time intact, in line with issues that the basal ganglia may have with action selection. Okay. So finally, we can present some evidence that even in healthy individuals, feed forward and feedback control can be completely dissociated from one another. Here, in this study, we presented individuals with a number of different sequences of force field environments that change from one action to the next. We can measure the properties of these sequences in 2 distinct ways. One is the consistency of each force field sequence, and the other is just the variability. So we could operationally define the consistency of a force field environment as the lag-1 autocorrelation of the environment. And so it captures how each of these movements are dependent on the previous one, or how what is present in one action is carried over to the next. In contrast, the variability would simply be the variance of the force field environment for each sequence. And so what we see is that the consistency of this force field environment can have a strong effect on the feed-forward adaptation rate, determining it for a large fraction of the variance accounted for, and there's a 90% sort of R squared for this relationship. So we see here there's a large difference in feed-forward adaptation rates for these different environments shown as the colored circles, but this is really largely accounted for by the consistency of the force field. If we look at instead the relationship between feedback response strength and the consistency of the force field, we see is that there's again a large variation in feedback response strength, but very little relationship to the consistency of the environment. In contrast, if we look at how feedback response strengths correspond to the variability of the environment, we see a really strong relationship here, accounting for 80% of the variance in the data across these various different force field sequences. But the relationship between variability of the environment and the feed-forward adaptation rate is either not present or really sort of a mild one. Okay, so together what we see is that the consistency of the environment strongly affects the feed-forward adaptation rate, but not the feedback response strength, and that the variability of the environment strongly affects the feedback response strength, but not the feed-forward adaptation rate. And this sort of double dissociation really suggests sort of really strongly independent control of feedback responses and feed-forward responses, even though they might share the same sort of internal model of dynamics. Now let's turn our attention to a very different optimal control problem that of sequential decision making. Now this is different for two reasons. One, that we'll use discrete rather than continuous time, proceed from one decision to the next. And the second is that instead of having an objective that's a sort of a pre-specified state trajectory, we're going to have an objective that's to maximize the total amount of reward, or the cumulative sum of the reward that will accumulate from one step to another. Okay, we're going to use this problem to provide an introduction for some of the basic ideas in reinforcement learning. Okay, so to motivate it, we imagine we have our squirrel back, and he's here in a tree, but instead of having sort of a single nut that he wants to get to, I would think that there are multiple nuts in the tree. In fact, there are not only multiple nuts in this tree, but there are many trees in the forest, and each of these trees can have multiple nuts in it. And some trees have sparse nuts, and some have dense, and some have small, and some have big, juicier nuts. And so the squirrel is going to want to sort of maximize sort of his reward, his satisfaction from eating the sort of the biggest, juiciest, most plentiful nuts that he can find, right? And so to set this problem up, we'll revert back to we'll use the basic sort of dynamical systems model, but in a discrete form, where we have some non-autonomous dynamics, where the state at time t plus 1, or time step t plus 1, is equal to this dynamics function of the state at the previous times, the state at time t, plus the action and the action that was taken at time t. Okay, this is formally known as a Markov decision process, which is a really sort of popular sort of formulation for discrete time systems. And so this discrete action could be a bite or a step or a jump. And so this squirrel could reach out to sort of bite this acorn that's just in front of his face here, or he could step over to this acorn or this one or this one and ready himself for taking a bite of them, or he could jump into this adjacent tree that's full of acorns, has a high density of juicy looking acorns in it. Okay, but let's just take a step back and think about what the state means here. So in this problem, the state is sort of inherently a little bit more complex than how we were thinking about it before, right? And so there's the state of the squirrel himself. So how much energy does he have to possibly to jump from one tree to another, or to gather acorns? More basically, sort of where is he? What was his location? Where is he? Where is he situated? And in what direction is he oriented to? What is he looking at? And there are things like what time of day is it? So squirrels are diurnal, and so they like to be out about in the daytime. So if it's close to sunset, he's going to want to sort of wrap up his activities and not do much more for the day compared to the morning where he's got a full day ahead of him. And then there are there are states that are like the time, other states like the times that are external, which is like sort of the configuration of the nuts in the tree that he's sitting in, and in some other, in the second tree, and a third tree, and a fourth tree in the forest, and then of course the locations of the second, third, and fourth tree relative to where he is. Okay, so it's quite a bit complicated, and so our objective, as I mentioned earlier, will be to maximize the total amount of reward, right? The total amount of sort of acorns eaten, or the total sort of goodness of the acorns, taking into account how juicy and tasty and large they are. And so we can think of this sort of total reward, capital R, as a sum over all time steps I of the incremental rewards received at each of those time steps, right? In fact, this problem is normally posed in a slightly more sort of broad, a little more complicated way, where the reward is taken as a summation of these R sub i's, of these individual rewards in each time step, multiplied by a function of this discount factor. And so here I'm showing a sort of an exponentiated discount factor alpha. And the idea is this discount factor would be a number between 0 and 1, and we raise it to the I power, right? And so if you raise a number between 0 and 1 to the I power, as I increases, the sort of exponentiated value will decrease. So for instance, if A was equal to 0.9, then at time step 0, when I is equal to 0, this discount factor, this coefficient on the reward would be equal to 1 to get the full size reward. At time step 1, this discount factor, this exponentiated discount factor would be 0.9 to the first power, which is 0.9. When time step was 2, this would be 0.81, etc. And so the idea here is that rewards that you can sort of get to immediately have a more sort of intrinsic value to you than the rewards that are more distal, maybe because there are intervening factors that means that you might not you might not get them, or they're just not as meaningful. So what's the optimal control problem here, right? So, again, given this dynamics, the state at time t+1 is equal to the dynamics of state at time t, and then the action at time t, and the objective function defining this discounted reward. What we want to do is can be really simply stated in that we want to choose this the action a at time step t that will maximize this total cumulative reward, right? Or to be more clear about it, will maximize the sum of the discounted rewards at all time steps. But there's a problem here, right? In that this requires sort of knowledge information about sort of all the future rewards, which we may not have yet. And so how can we attack this problem? And the most common way to do this is to define what's known as a value function for each state. Okay, and so we define this value function v of the current state. That's the total future reward expected for each state, right? So and if we have this, then this value function, then control is really easy. What we're going to do is we're going to choose the action that takes us to the highest value state that we can reach from our current state, right? And so we would simply choose some a of t that will maximize this value v of the dynamics of s of t and a of t, right? And of course, these dynamics give us the next state. All right. This choice of strategy is often referred to as a policy, right? So the idea is we have some policy pi that will choose a of t given information about the state, right? Given the dynamics and the value function. All right. So, but how can we determine this value function? And the value function is the sum of total future rewards. And so if we write this, it would just be the summation of the reward at each time step multiplied by the this discount factor raised to a power that's how far away that the time step is from the current time t, right? So if I goes from t to small t to capital T, this value function at time t would be this alpha of I minus t, which is how far in the future I is away from the current time t, right? So we can do a little math on it, right? And just expand this summation in a simple way where we take the first term, break out the first term of it, right? And say we have the summation of i's from little t to little t, which is just a single term, of r of I times a to the I minus t, plus the terms, the additional terms that come in the future, right? So that's I is going from t+1 to capital T of r of I times a to the I minus t, right? And so if we do this little trick, what we can sort of realize is that the second term, right, can be sort of simplified by pulling out a simple alpha, pulling out alpha to the first power. And if we do this, what we get is we get an alpha out here, and we get the alpha terms remaining in the summation instead of being alpha to the I minus t or alpha to the I minus t+1, right? And then if we look at this new expression inside the parentheses here, what you see is that this is sort of identical in form to the original form of the value function, except that this little t is being replaced by t+1, right? And so this tells us that the value of the current state is equal to the reward achieved at the current state plus alpha, which is outside the parentheses here, times the value of the next state, right? It turns out to be a famous equation that it's called the Bellman equation. Okay, so the Bellman equation is really great because this recursive single sort of time step definition for the value function turns out can be solved by a really powerful technique called dynamic programming that basically goes sort of backwards in time using information about sort of future values to build on what the value would be, to build up what the value would be at the current time, and so this is how lots of sort of reinforcement problems can be solved and approached. I hope that the stuff that we went over today was helpful to some of you guys. Gives you some sort of insight for different ways to think about control and optimality and control. And I just wish you guys the best.